I can start when you tell me to, but since this is a different computer with a different recording level setting, let me ask again, am I audible now?
Yes, Ananda, your screen is also visible and you are clearly audible.
Yeah, and I realize that my speaker is turned too high because earlier I was not getting hurt by anybody's comments, but now Onaboda's statement really hurt my ears. I have to reduce the speaker setting. Okay, now that I've changed this, Onaboda, can you repeat that once again just to check?
Your voice is clearly audible.
Okay, good. Okay, so
okay, good.
I will start.
Let's
Get rid of my
Ananda, your
picture.
video is on. Do you deliberately?
No, I switched it off right now. It comes on by default. I just forgot that the video is on and the audio is off by default. Okay, so I'm switching off the video and now I'm going to start. Okay, so as I said, we are going to now discuss a program based on the thing that we talked about. And let me just actually show you what the program is. I remember I showed you this program in the very first lecture that I had, promising that at the end of the session, you should be able to understand most of this program, if not all of it. Well, this is what the program is. So let me just show you the full extent of the program. It looks long, but if you remember, okay, I'm just showing you this directly without opening the program itself. I'm just showing you this directly from the website. I hope this font is okay. If not, maybe I can increase this a bit. Yeah. Now the program looks long, but you have to realize that this string, for example, the one written in triple quotes. Just to remind you, a string in triple quotes allows you to write multi-line strings, but it has actually a much bigger usage. These are doc strings. These can be used as documentation for whatever module you're writing. This file called network.py, network.py, is actually a module which has lots of useful, well, not lots of useful programs, but basically the program that all the useful functions that we are going to need for doing basic machine learning, implementing the neural network I've talked about a while ago. And this, for example, this triple quoted string essentially just talks about what this is. It's a documentation line. So when the program is run, the computer will simply ignore these lines. But when you ask for documentation using help, these are going to be returned. So these are very useful for writing helps to both yourself or other users. These, of course, are standard comment lines, the ones which are preceded by hashes. Maybe we did not mention that, but if you write a hash in front of a line, that line is commented out. And this is a standard library which is being imported. You have already seen the random library. There's a Python random library. Not even NumPy is random. It's much simpler than that, and just generates random numbers which we will need for our stochastic part or the stochastic gradient descent. And then we need to import NumPy as NP. And the whole work is done by an object called network that we are going to write here. Now, as Onaboda talked about before, it's you define an object by using the class keyword, then you give its name. Network is the name of the object that you're describing. And within the brackets here, you don't really give an argument. You essentially say what kind of other object this object inherits from. If you don't know what that is, don't worry about that right now. That's not really very important. What is important is this idea that an object is sort of like a box. It has methods, things you can do to it, and it has some attributes, some data which it contains. So frankly, this is a distinction which has to be clearly maintained. An object can have both methods and attributes. Attributes are just fixed data. So for example, for a NumPy array object, ndim is just an attribute. So that's why you don't say a.ndim bracket. The bracket would be calling a function. However, there are many methods which you have used with arrays. Anything which you write array dot, say np dot load text, that's an NumPy method, and then you follow it up with an argument. Anyway, when you define a class, the first function in the class is for, okay, this is for people who have done object-oriented programming in, say, Java. The Java requires something called a constructor, which constructs when you when you instantiate the class, that is when you create an object, instance of this object, the constructor functions creates the instance. Technically speaking, Python doesn't really have a constructor, but the technical difference is really not important. What is important is when you actually first create an instance of this object, this function, whose name by convention is always _init _, is called. This always has at least one argument, which is self, which is just refers to the object being created. So when you call the network function, this function is this init is called. When you call the network, you try to create the network element. This function is called, but you don't give it self as an argument. You don't have to, self automatically goes in. But you have to give this second argument, which is there here, sizes. So here again, you have a rather lengthy triple coded string, which essentially talks about what is there in this, what this function does, and it describes this rather beautifully. So all you have to do is read this to understand what this does. But notice that the moment you call it, several attributes are created. For example, sizes is an array, and here the object, which is our network, immediately gets some attributes like num layers. Num layers is number of layers. So it's obvious that if you have a 3-element array as an input, you're going to end up defining a 3-layer neural network, which means one input layer, one output layer, and one hidden layer in between. Of course, if you give a bigger array here, you will have more layers. But frankly, remember, this program is sort of rudimentary. It does not take all the shortcuts that speed up the programs, which is why you should not really play with this with huge number of hidden layers. That will make this way too slow. And this instance, whatever you create, will end up with having an attribute sizes, which is the same as the array which you give, which essentially holds the sizes of each of the layers. And then you have biases. Now you don't have biases for all the layers. You only have biases for the hidden layer and the output layer. The input layer, of course, just takes the input numbers. It doesn't have any bias because there's no calculation done there. Which is why what you're doing is the moment you're creating the instance, you're creating this biases attribute by taking from the NumPy random, np.random, this random, which basically takes two arguments. One is sorry, y, so comma 1. So y comma 1 would mean y here is in sizes 1 colon, y 1 colon, sizes 0 is not used. Sizes 1 colon means basically you drop the beginning, the first term in this array or list sizes, and you end up with basically, suppose, okay, let me just give you an example. If my sizes array is say 2, 3, 4, that means I'm defining a neural network with 3 layers, 2 neurons in the input layer, 3 in the middle layer, the hidden layer, 4 in the output layer. And sizes 1 colon will simply be 3, 4. So what happens is when y takes the value 3 first and 4, this is a list comprehension, so it takes it for both. So you get a list with 3, 1 array of random numbers, which means 3 one-dimensional numbers, so 3 biases for the 3 intermediate neurons. And when you go to sizes 2, that's 4, the value is 4, you get 4, 1 random, which produces a 4, 1 shape array. So so you get 3 biases and 4 biases. 3 biases for the middle layer, 4 biases for the next layer. I'm not sure whether this has been explained properly before. Sizes, okay, this is pretty easy to see. So let me just give you an example of what this really means. I've just started Python here. So let's say I take an array called sizes, which has let's import numpy for them. Let me just demonstrate what this tape is going to do. The good thing about having an interpreter is that you can always use the interpreter to figure out what things are doing at any given stage. So notice sizes. Okay, I'm not going to go through every step this way, but I'm essentially showing you this because if you want to follow the code yourself, this essentially is the kind of thing you should do. So what is sizes 1 colon? That's the slicing that we have all learned before. This is, of course, this slicing, not array, but the same idea works. It's just 3, 4. And so if I say something like random is normally distributed random number, which you have seen before, Abhijit's class. And the argument which I'm giving here, y, 1.
Random spelling.
Oh, I messed up the D. Thank you. Random. So random, of course, is a submodule of NumPy. And from that submodule, I'm taking the random function, which is the normalized random number creator. So to this, I'm giving an argument. What is that? Y, 1. And that is for y in so sizes 1 colon, of course, is an array with 3 and 4. So first y will be 3, then y will be 4. And what's going to come out are, okay, this becomes a bit difficult to read. But what you see here is this. You first get a 3, 1 array. Then you have a 4, 1 array. Oops. Need to move the, okay, I need to move the thing up. So you have a 3, this is what is returning is a list which has a 3, 1 array as the first element. That's because sizes 1 was 3 and a 4, 1 array as a second element. So these are the 3 biases for the middle layer, 4 biases for the output layer. On the other hand, let's try to break up the next line a bit. Let's try to understand this line in pieces. So first there's this sizes colon -1, sizes 1 colon, which we all know what they are. But I'm not sure whether you have seen zip before. So zip essentially does this. If you give zip, say, 2 arrays, or even more than 2 arrays, suppose I give it 1, 2, or not necessarily arrays, any iterables like this. So here I've given 2 lists. So what it does is basically it produces tuples with the first element from every one of the array. It packs them together in a tuple. Second element in every one of the arrays. They pack them in another tuple, and so on. So this is what zip does. If you have a bunch of different arrays or lists or tuples, it takes the 0th element from each one of them, makes that into a tuple, then the 1th element, then the 2th element, and so on, and returns them all in a list. This actually is very, very useful for many purposes. Especially if suppose I want to run a loop with over 0, 1, 2, 3, let's say, and for 0, 1, 2, 3, I want a particular string to be apple, banana, etc., etc. Then what I can do is something like this. Or and this is the important thing about for loops in Python. They are actually much more powerful than for loops in most other languages. So for I comma fruit in. So now I have two indices. Zip. I'm zipping together two lists, one with just 0, 1, 2, 3, the others with and I've given only 3 here for the simple reason that I'm not a big fan of fruits. So I have 4 elements in the, also to show you what happens when there are different lengths in the list. Then zip will actually pack together 0 and apple, 1 and banana, 3 and grapes, and simply drop the 2 and grapes, and simply drop the last 3. Say print. This is Python 2, so print is just like a command. Fruit. What happens is for each pass, I and fruit both get the values. So this is unpacking, right? Remember, once you zip them, you have a list of tuples, and those tuples are unpacked into the 2 variables I and fruit every time the loop goes through. And so I get 0 apple, 1 banana, 2 grapes. Now this may seem like a trivial example, but this actually becomes very, very useful in the long run. And for example, right now, if I just did zip, so it says size colon -1. It means the last one is dropped. And size 1 colon, the first one is dropped. Oh, I forgot that I did not define size yet. Did I? Oh, sizes. I wrote sizes. Sorry. Now, can you realize what these 2, 3, and 3, 4 are? Of course, what they are is simply 2 from 2, 3, and 3 from the 3, 4 back together, and 3 from the 2, 3, and 4 from the 3, 4 back together. But what do they mean in the context of the neural networks that we are talking about? Remember, when I put in 2, 3, 4 as sizes, I get not okay. I should have put them in a size, but doesn't matter. Whatever argument you give. If I give 2, 3, 4, that means I have 2 elements, 2 neurons in the input layer, 3 in the middle layer. So how many weights will I get between the input layer and the middle layer? Each of the 2 neurons in the input layer should be able to talk to each of the 3 neurons in the middle layer, and there will be edges for each one of them. Each one of them will have a weight, which means I should have 6 weights, which should come in a 2 by 3 array. 2 by 3 because the first 2 refers to where they come from, and the next 3 to where they go. Similarly, you have 3 neurons in the middle layer, 4 in the output layer. So 12 weights that should come in a 3 by 4 array. And that's all this thing is doing. It's just initializing the weights using random numbers, normally distributed random numbers with sizes taken with array sizes taken in such a way. So here notice you are taking y comma x, whereas this is x comma y. That's because I want the row column in the proper order. So I want 3 rows and 2 columns, etc. instead of 2 by 3. So that's why you are done for xy in zip this and yx. If this is not clear, I urge you to actually try it out yourself. It should be pretty obvious. You're essentially producing random weights of just the right size for each layer to layer connection. So next one is straightforward. How do you calculate the feed forward? That is the next step. There's another method. So that method, the earlier method was simply the init. That's called whenever you create an object, instance of the object. Next functions are what you do, what you can do to the function. Feed forward is something you can do. It just takes in the weights, takes in A, dots them together to produce a column vector, adds the B column vector to that, and produces, applies a sigmoid function. So this is how you go from one layer to the next. That's why it's called feed forward. The A's for one layer, they are dotted with the, this dot really is matrix multiplication. I'm not sure whether we have covered this in detail, but this dot essentially is NumPy's way of carrying out ordinary matrix multiplication. And when you do this, this is really the matrix of W's multiplying the column vector A added to B. And that's the Z. You apply the sigmoid function to that. The sigmoid is defined later. And then you get the output for the next layer. So this is how you go from one step to another. Well, this is the stochastic gradient descent step. This is the one which I'm going to use soon. So training data, this comes, remember the self argument you don't have to give, that's automatic. Training data, you have to give. Epochs, which is how many times you're going to run this. Epochs, remember, is not one mini batch running, but if you have 50,000 training data, then out of the 50,000, if you have a mini batch size of say 10, so only 10 at a time, then each epoch will be 5,000 such mini batches running, which means in a way you're giving every one of the inputs a chance to feature. Of course, if you're going to sample them randomly, so if you sample 10 elements randomly 5,000 times, some will come multiple times, some will not come at all, but you're essentially giving 50,000 inputs. That's one epoch. The next argument is the learning rate. And finally, I have to tell the computer what the test data is. If you don't tell it what the test data is, it's not going to run with the test data. It's not going to test at that stage. If you give it the test data, it essentially at the end of each epoch, it's going to test against the test data and figure out how good or how bad it's doing. And then what it does is things like if test data means if test data is defined. Remember, test data was defined to be none by default. So if you don't give the test data argument, it's none. And if none is always false. So if test data means if somebody has given a test data value, then it's not none. Then number of n test is defined to be the length of the test data, how many test data elements you have, and so on. N is the number of training data examples given. And this runs that many epochs and so on. Let me just point out that certain functions from the NumPy module, or this is from the random module of Python which is being used, is a random shuffle, which takes the entire 50,000 input elements, shuffles them around, and then it just takes a slice. So slice, once you shuffle it, you get a random set, and then you go from 0 to so this for k in x range 0 to n in mini batch size, that means k becomes 0. Let's say mini batch size is 10. So k becomes 0, 10, 20, 30, 40, and so on. So this actually gives you splits it into mini batches from 0 to 9 first, then 10 to 19, then 11 to 29, and so on. So it's essentially randomizes the set first, then picks out batches. And for each batch, it does the self-update mini batch. Okay, so I'm not going to go through all of this, but what does update mini batch do? It essentially calculates nabla B and nabla w, which is the gradient with respect to b and gradient with respect to w. How does it do that? By essentially calling the backprop method, which is the final mathematical piece in all that. And then it essentially does NB plus DNB. So it moves NB by DNB amount. That's roughly it. Okay, all the details I don't have to go through right now. The backpropagation algorithm written down here essentially calculates using NumPy all the partial derivatives in a very fast, quick manner. So this is the longest part, but most of it is pretty easy to understand. So this is the sigma prime, for example. You are carrying it out on the entire array Z and so on. And well, cost function essentially, finally you have two functions called the sigmoid and sigmoid prime. I'm not going to describe the entire program, but I assure you that all the Python you have learned in this entire workshop, if you just stick to that and nothing else, and maybe if you meet something which you have not learned yet, you can always Google that up. It should be pretty easy for you to run through the program and understand the whole thing. And the only thing is that you need one more program to run this, one more thing, which is you need to take the MNIST data, which is in a zipped up archive. You need to open it using gunzip, which can be done from within Python using the gzip module. And then you can shuffle that around, break it up into 50,000 training, 10,000 validation, etc., etc. All that is done by another utility program, which is there in the same directory. So let me just show you that this is basically, I have just gone to GitHub where all the code is downloaded and opened it out. So I'm getting a directory called neural networks and deep learning master file, which is the file which Nielsen's GitHub account provides. Inside there's a directory called SRC. I'm going in there. This actually has not only this program, it has other improved versions which Nielsen talks about as he goes further and further along in his book. I'm just going to use network.py, the simplest one, and mnistloader.py. These are the mnistloader is just a utility function, module, which provides a way of essentially taking the MNIST data, MNIST source files which are already there on my computer. Of course, I could write code which would download them automatically from the web and then open them and all that. That can all be done using Python. But the simple thing is this is already on my hard drive. Is going to expand that out because they are compressed, and then split them up into random. The 60,000 training data is going to split randomly into 50,000 testing and validation and so on. The mnist.loader_loader_py.file is also there in the same directory. And if you open this out and read it, it should be pretty easy to understand what it does. So I'm going to now run the program for you to show what it does. So I've called Python. This is the interpreter, of course. And in the interpreter, I'm going to first get the training and test data available. So MNIST loader. This is the name of the module which has been written here. So that's why it's already in the Python file in this directory. I'm importing that. And then I'm going to use a particular method in that module, which I'm not explained, but I've already told you what it does. To split up my set of MNIST pictures, total 70,000 of them, into these three sets: training data, validation data, and test data. I'm going to call them from using MNIST loader. Of course, now that I'm having difficulty typing it, I might have considered importing MNIST loader as something else, as a small shorter name, but anyway. And there's a load_data underscore wrapper program there, which by default does a 50,000, 10,000, 10,000 split among these three variables. So it returns a tuple with 50,000 pictures in the 50,000 arrays basically in the first zeroth position, and 10,000 in the second, 10,000 in the last. You can change, you can give arguments which will change these numbers, but I'm just going by the default now. So it's taking some time, but now it's done. My tr underscore dat, for example, if I look at what this is, I've already gone over time, so maybe I will take 10 more minutes. Is that okay?
Okay.
So this is a list. And how long is the list? It's 50,000 elements long, as I promised. And if you look at the 0th element, for example, okay, that's long. So let's just look at what that is. That's a tuple. So every one of them is a tuple. In fact, how long are the tuples? They are 2 elements long. Why 2? Because each tuple has 2 arrays. One is the actual picture. The other is the array. The other array is the shorter one, which you can see right now here. So can anybody tell me what this is? The second array, which essentially is 0, 0, 0, 0, 0, 1, then 4 zeros. What is this second array here? I've already described what this is. The 10 element array with only 1, 1.
5.
There's a label. This says that this particular picture is a picture of 5. Okay. And so if you look at the 0, 0 element of the tuple, that's 784 elements long. That's the picture data, scan picture data. So each element in the tr underscore dat is a tuple with 2 entries. But the first one is a picture itself, 784 elements. The second one is a label. So every one of these are labeled. They have a label which tells the computer what they are. Of course, that's how you train this. You know exactly what this thing is. So you know whether your program is doing well or doing badly. So now that we understand this, this training data, each one of tr underscore dat, te underscore dat, or val underscore dat, somebody's, hopefully it's not mine, somebody's microphone is making a lot of noise. Okay, so each one of these has the same structure. Every one of them have tuples, 50,000 in the first one, 10,000, 10,000 in val underscore dat and t underscore dat. And each one of them are tuples with 2 entries. The first one is the array which contains 784 elements, the picture itself. The next one is the label, which tells you which number it is supposed to be. Okay, so now that I have the data, let's import the network module, which is the function you just saw. And then we create an instance of the network object. So in the network module, there's a class called network, which is capital N. Remember, when we are creating this, we have to give, we'll look at the init again. The init, which is at the beginning of all this. Yeah. This takes 2 arguments, self and sizes. Self is a reference to the object itself, which is being created. So when I'm saying net equal to, net is the name of the variable, this is going to be the instance of the network object. Self refers to that. So when I give the argument, I don't have to tell that any longer. I just have to give the next argument, sizes. So sizes, what do I have to do? I have to specify the sizes for my input layer, hidden layer, and output layer. So input layer, all the inputs. How many inputs do I have? 784, 28 by 28 pixels. In the middle, I will give, say, the picture had only 15 layers, so I will put 15. And the output has to be 10. So this is how you just call it. I've created a network. This essentially is done. I've created a neural network with 3 layers, 784 input neurons, 15 middle neurons, hidden neurons, and 10 output neurons. Then all I have to do is just this. The stochastic gradient descent, SGD method, that has arguments. If you look at the arguments there, let me just remind you what the arguments for SGD were. The first argument self, again, is actually net. You don't have to call that. You don't have to give that. Then you have to give the training data first, then epochs, then mini batch size, then eta. These are the 4. How many times do you have to? Epochs means, each epoch means you're running the thing 50,000 times. But in mini batches, smaller mini batches, not all of them at once. That's the stochastic gradient descent part. Eta is the learning rate. And test data, this is the only one which has a default value. You can omit this, but if you're omitting this, then you don't get to see while the program is running how well you're doing. So what we will do is we will give the first argument, which is the training data. Next argument is a number of epochs, let's say 20, let's do 20 epochs. And give 10 mini batches. 10 is the size of a mini batch. So we have 50,000 things, but we are only taking 10 at a time. But we are going to repeat that 5,000 times in an epoch so that I actually give all of them a chance. And then I put in the learning rate. Let's say I choose 3. I choose 3 simply because Nielsen chose 3 in his example. You can play around with that. And finally, the one argument which is a default value, test data. I want to see how my program is doing while it's running. I will just give e_dat for that. And let's hit the enter, and you will see a neural network at work, and you will see immediately how many numbers, how many things, how many out of the 10,000 test data is getting right. So it takes some time to run, of course, and mine is a slow machine also, but that's really not long given the amount of calculation it's doing. And anyway, the first initialization will be done only once. So the first thing also always takes a longer time. I just hope my computer has not frozen up on me. That's one possibility. Yeah, it's working. So in the very first or 0th epoch, it got 8,898 of the 10,000 right. Not very impressive, only 88.9% accuracy. But given that the test data has very crude pictures, this may not really be very bad. So if you keep on going, this will keep on taking some time. It's improving. It's sort of going to more or less improve over time. I'm using only 15 intermediate layers, so that's Nielsen actually used 30 and he got 94% accuracy. My guess is I will get around 91, 92%. But that's the thing running on its own, and it's going to keep on running. Let me just, for the time being, so I've got around 91% accuracy in just the third run. I'm going to run this 20 times over, so it's going to take some time, but now is the time when I can take questions. So I'm done. I have to go back to the meet. So if anybody has any important questions,
when you divided the data into taste and validation and training, do you have any option of going for cross validation?
Cross validation, no, not in this version.
Oh, I see. Thank you.
But there will be later. Nielsen's book actually talks about that later.
What is cross validation? Tell me one.
Cross validation is changing the the one you use for training. For the next time you use it for validation. I mean, just shuffle that.
Okay.
So that can be, that actually is effectively done anyway, because you essentially take all the set and then you shuffle it at the beginning of every epoch. But yeah, this doesn't formally cross-validate. You can of course put that in. That's pretty straightforward. This program has been written to keep most of those frills out. This is just a bare bones thing, and let's just see. While I'm answering questions, I've got to 92% roughly. It's not going to be a steady increase all the time. After all, it's stochastic. So sometimes it's going to go down a bit. But around 92% is what I'm going to get with this neural network. I can do better by increasing the number of neurons. Of course, the only one I can really increase is the middle layer, because the input has to be 784, output has to be 10. Of course, I can also go with increasing the number of layers, but that's going to be very slow on this particular implementation. Because this doesn't take any shortcuts or speed ups. This just brute force calculus using neural network basic algorithm.
But it is why it is after improving upon up to third epoch, why it is again going down? I mean, maybe
it's not going down. It has just gone down a bit.
Yeah, not going down. When
that's
9196 to 91.
It's going to be around that. It's going to fluctuate around that.
Okay. Because of stochasticity, but not in the initial period. Not in the initial period.
Initial is learning. So it's learning.
From 0th epoch to 3rd epoch, you see the steady increase.
But that's because the weights had initially you started with completely random weights, right?
Yes, that's
so
okay.
Just went through one
After
pass.
that, it is improving.
No, this 8898 was not with random weights. With random weights, you would have got 5,000. Say, you would be lucky if you got 2,000 right.
Okay.
This was after epoch 0, which means the weights have already been learned a bit, but only one pass. So as you go through more and more passes, more and more epochs, the learning gets better. But although the learning gets better, it's still stochastic. So it's not going to be steadily improving.
Okay.
But it's going to improve in the long run.
Yes.
So again, how many epochs would you run this? Would you stop at 20 or would you go on to 30 or 40? Again, all these are matters of detail, which depends more on which particular thing you are using. Okay, so are there any questions about this? Because this will keep on running, and this is rather uninteresting to see this unless it's on your own computer. If it's on your own computer, it sort of gives you a sense of fulfillment that you have actually run something and it's working and so on. Even better if you wrote it yourself. This one I didn't, but as I said, you could just use once you've learned this using a bare bones Python program, you could just go on to Keras or TensorFlow and write this whole code in 4 lines or 5 lines. And then a typical Keras program will be, say, 20 lines with other improvements thrown in. But in 20 lines, you will get a fully working neural networks.
Ananda, I have a request to you that after the session, in our WhatsApp group, please share some information about the use of machine learning in physics.
That's way too vast, right? But one thing is, say, nowadays astrophysics, for example, all the astronomical data, there are way too much data. So you have to identify clusters or structures. Wherever you need to identify structures. So as I said at the beginning, LHC or any large collider experiment. Too much data, you have to make sense out of it using structures. You use machine learning there. Astrophysics, you use machine learning in a huge way. Biology, of course, you use machine learning a lot. So in fact, you do machine learning a lot in, say, remote sensing. Any situation where you have the point is you have to have a big amount of data to begin with. Otherwise, machine learning falls flat. So things which either have a big amount of data simply because there is a huge amount of data naturally, or because you can generate a large amount of data. So near the very beginning of the COVID pandemic, there was this talk about somebody, a few students from a university finding out a machine learning algorithm for detecting COVID. Essentially what they did was, I didn't read the paper but I saw newspaper reports, and from that what I gathered was what they did did not work simply because they did not have enough data at the time. But in principle, if you have the sound of people coughing, lots and lots of them, and you know that some of them have COVID, some of them don't, so they're already labeled, you can change that coughing sound into an electrical signal, which of course we can, and digitize it, and then feed it at the input layer, and then essentially let the system learn what exactly is a COVID cough like as opposed to an ordinary cough. And it should work. The only problem with that would be you need enough people coughing, enough data. Unfortunately, with a new pandemic, data is at a premium, and you don't. And now you have a sort of problem. You don't really want more people to fall sick, but unless more people fall sick, you don't really get your data. So it's sort of for all things. Say, for example, for cancer detection, nowadays, reading X-rays and detecting tumors, machine learning systems do it much better than most human practitioners do. All that they need was old data with lots and lots of X-ray plates labeled with there being a tumor and not being a tumor. And you set up a neural network, play around with it, and now you can get around 95% accuracy in prediction, which is actually better than most doctors can. Not most doctors, in fact, almost very few doctors can beat a machine learning program there. Of course, in all this, what you need is a huge amount of data. So just a personal anecdote. My own trace with machine learning proper was very, very short. It was for a period of a month or so when I visited John Jay College of Criminal Justice in New York. And there I worked with somebody who was there's somebody saying accuracy can decrease with increasing number of epochs. Not really. The increasing number, this is stochastic. Well, now it's sort of steadied out. It's not going to show you any great improvement or deterioration. It's around 92%. The small decrease or increase you're seeing is basically random fluctuation. What happens is initially it learns, and once it has learned, there's nothing much more to learn. So here maybe it's even good that I could even stop it here. If I had actually run with a larger, say, just to show this, if I had set up the network with, say, maybe 30 neurons in the middle layer, in the hidden layer, to double that, and then run with the same mini batch size and everything. This, of course, is going to start all over again. And then you get then you should see this performing better, at least after a few epochs go by. Now, okay, going back to my personal anecdote, I worked with somebody who actually happened to be a very well-known quantum chemist at one time, but he had switched over and become a forensic scientist, and he was actually using machine learning. At that time, it was support vector machines. They were the big thing in those days, to try to essentially identify tool marks. And he told me another nice story. I asked him, why are you doing this? After all, human beings, even at that time, the state of the art was such that human experts were better. He said, well, the problem is when a lawyer asks a human expert in court, fine, you are saying that this tool mark was made by this tool, but can you explain to the court exactly how this works? Then the fellow usually couldn't manage to. And sometimes cases got thrown out because of that. The human expert can do much better, but the human expert may not be able to sort of justify what he is using. We do these things intuitively. We know that this is correct. Being asked to explain why this is correct is difficult. Then he said, well, after all, lawyers are lawyers basically because they can't do mathematics. I'm pretty sure that's not true. But anyway, he said this. Lawyers have become lawyers because they can't do any mathematics. So if you tell them that this is the support vector machine algorithm with the kernel using this and that shuts them up. No lawyer would ask you anything after that. So here, of course, this thing is happening slowly, but it will eventually become better than our previous case. It's of course much slower because you have, the moment you have doubled the number of middle neurons, you have actually doubled the number of weights. Now, if you have 12,000 weights, you have 24,000 weights and that many more calculations. Okay, but the final part of the anecdote is this. I picked it up a bit, not much at that time. Came back to Calcutta, of course, after 1 month. And then I thought that I would try this in fingerprint analysis. And Calcutta should have been the best place to do this because I'm pretty sure most of you know this, at least Shizu Jatha in Shonarkella has informed everybody that fingerprinting started in Calcutta. This idea that identifying criminals with fingerprints was discovered by Herschel in Calcutta. And so I thought we should have a pretty extensive fingerprint library. And if that was already digitized, which is the case, we could easily set up an automated detection system. So I approached Najrul Islam, who was the police commissioner at that time. And he rather regretfully told me that, frankly, the data keeping is abysmal. So we don't have enough data to actually write good enough machine learning code with those things here. Of course, with on the other hand, things like LHC code, one great thing is you can actually simulate LHC using other programs, simulate what will happen when collisions take place, and take those signals, simulated signals, and use them to train your computer. So now you have software training software in a way. As you can see, we are at epoxy already. We have got to 93%. This thing sort of plays out around 94.
Ananda, in machine learning, also people do such thing. When they have shortage of data, they can do different kind of transformation on the available data to generate more.
Yeah, they can, but that's a bit. Yeah, that's true, but that's a bit more sort of incestuous and prone to small errors in the original data set sort of blow up very rapidly. So there you have to be very careful. You can, of course, have many clever ways of increasing. As I said, you can teach neural networks to play games by playing games against each other, against itself, and learning the rules better. I think I've gone way over time, and I think I should stop now. But you can see the program is running and sort of approaching 94%. How do we know whether the network is overtrained or not in this case? That's what the validation data is for. You switch, it works wonderfully on your test data. You switch to validation, it fails. It shows that your program has sort of essentially learned the test data by heart, sort of mugged it up. And then it fails in anything new. That happens whenever people mug up. It happens also when computers mug up. So I think I'm half an hour over time, so it's definitely time that people go and have tea. So I'm waiting for a signal from our secretary or whoever.
I think the convener has left. He joined, and he left.
Okay.
Maybe he has to join another program.
Okay. So yeah, he is very busy.
The convener, we can then call it a day, and it was and let us all thank